Hi, I'd like to do one disordered tetraethylammonium from the structure that we were looking at in class on Thursday so that you have an example to refer back to. I'm in a folder with the ints and HKL files, and you can see in the ints file that I already included the two ordered tetraethylammoniums in this model. So I'm going to run that refinement. And we're just going to pick the most prominent remaining disordered tetraethylammonium and build a model for that one. So I'm going to select Q1. We'll see where that is. It's over here. I'm going to double click on this whole thing, show this fragment only, and remembering the philosophy of going back lots to add atoms and make new difference maps, I'm going to start by just adding the nitrogen atom in the center. So the nitrogen is directly on the symmetry element, and that could give us some hope that maybe it will not be, this atom won't be disordered. So I'm just going to put it in fully occupied. This is in 61, type 3, and the coordinates 1, 1.5. And we'll run this refinement. Okay, here we are down here. I'm going to grow this out and try among these Q peaks to identify 4 that are in a tetrahedron around the nitrogen atom. So I can see that there's sort of a cube around the nitrogen, or roughly a cube, which you can imagine as 2 tetrahedra superimposed on each other. And I'm just going to pick 4 kind of not opposing, 4 out of the 8 corners of the cube. Well, I'm going to pick a tetrahedron is the short way of putting it. The one that I just picked, I'll delete these 4, and we'll use the other 4. Okay. I'm scrolling down a bit to get a few atoms out of the way, and now we can see our tetrahedron a little more easily. So we're going to remember that these go in a negative part number. They're on a two-fold symmetry element. I forget if this one is a rotation axis or an inversion center, but they both have a multiplicity of 2. So this occupancy is going to be 10.5. And these are going to be carbons 62, 64, 66, and 68. Some of these Q peaks are symmetry generated and some are not, but that doesn't make the slightest bit of difference because we know that the difference map has the full symmetry of the space group. So that means we have no idea, are we going to locate the peaks that we want as themselves or as symmetry equivalents of themselves. It doesn't matter. In reality, it doesn't matter what you call any of those peaks. Let's add some restraints to make sure that this is going to stay chemically reasonable. Right now, we're going to put a 1.5 angstrom defixed restraint between N61 and each of those carbons. We'll run this refinement. Okay, the tetrahedron stayed where it belonged. That's a nice thing to see. Let's grow this out right now. I'm going to find my 4 symmetry generated carbon atoms and delete those, leaving only the original 4 positions remaining. And now we do have 4 positions of the methyl groups that we can see. So these are the 4 Q peaks that we're going to use, and this is actually a lot easier than it sometimes is. I'm going to label the carbon atoms to make our job a little easier. And I'm going to put each methyl after the corresponding methylene. So C63 comes after C62. Here's C65. And finally C69. Okay, so now we've actually run into a bit of a dangerous situation that we need to be careful of, because these are just 2 Q peaks plus their symmetry equivalents, and the difference map is telling us that pair by pair these methyl groups are sitting on top of their own symmetry equivalents. So that's a potentially unstable situation because you have 2 independent atoms starting on the same position. So one thing that I'm going to do to try to be careful of that situation is systematically move these atoms just a bit off of their starting positions. I'll take only the symmetry generated ones, which are C69 and C65. I'm going to tweak 1 coordinate in each one of these by a couple thousandths. So I'm changing 591 to 594 on C69, and I'm changing 577 to 573 on C65. So now the pairs of atoms and their symmetry equivalents are not quite on top of each other. And I'm adding a defix restraint as well to stabilize the geometry of those methyl groups. This is going to be between each methylene and the corresponding methyl. So that's C62 to 63, C64 to 65, 66 to 67, and C68 to C69. And I missed a letter here. Okay, let's save this. We'll try this refinement. Bad atom or unknown instruction. What does that mean? Okay, we'll do this the official way. Let's look at the list file. Go down to the bottom and see where was it before it got angry. Here we are. C63 doesn't have an atom type number. So I'm going to put a 1 there, save that again, try this refinement. Okay. How did we do? Type labels to get them out of our way. Okay. Okay, here we are. Everything, all the ADPs are stable. The bonding distances are all pretty reasonable. Here's a bit of an oddball carbon-nitrogen distance, but it's not too severe. One thing that could behoove us is to try moving the nitrogen just a bit off the symmetry element and put it in the disordered part, and see if this improves the model at all. I'm adding a bit to each of the coordinates of the nitrogen atom. And we're going to repeat this refinement and see if the R factor improves very much, basically, and see if the geometry is more consistent when we let the nitrogen move off the symmetry element. Right now we have our WR2 3362. And now that we're releasing the nitrogen, it's still 3362. Did I save that? No, I didn't. Okay, we went from 3362 to 3359, so I would not call that a significant improvement. Although I can see that the nitrogen-carbon distances became a little more consistent, so that's arguably a nice sign. And we can ask ourselves, how far off the symmetry element did that nitrogen move? I'm going to type pack and show, wow, this looks kind of cool. I'm going to show just one of these. The nitrogen actually moved pretty significantly off the symmetry element. It moved by about 0.1 angstrom. And it moved in the direction, I would assume, of that one carbon that was a little farther, had a little bit longer carbon-nitrogen distance than we expected before. So as long as the anisotropic ADPs refine stably when we leave that nitrogen in the negative part number or off the symmetry element, then I think we should leave it that way because it gives us a more realistic geometry. We'll check on those ADPs by typing anice 9 here. We'll put a Rigu restraint on these atoms in 61 through C69. And I will also come up to the top and add hydrogens to those. Each fix 2, 3, C62, 64, 66, and 68. And each fix 1, 3, 7, the odd numbered ones. All right, how's this going to look now? Well, we have a couple ADPs that are a bit unrealistic or a bit unstable. We remember that a couple of these methyl groups were overlapping with symmetry equivalents of other methyl groups. And we can see this kind of characteristic pair of one that's way too small and another that's way too big. So let's add a simu restraint alongside the Rigu restraint. A lot of times this will clean up that type of problem. And we'll apply it to the same atoms. Okay, well that's a bit better, and it's nobody is gonna complain when they see this. You know, here's another thought actually. Depending on the type of symmetry element that this is sitting on, we may, this is, oh, not that. This is on an inversion center. So that means that these overlapping pairs of atoms are inversion related. And since an ellipsoid is centrosymmetric, that means these inversion related pairs should share an identical ellipsoid. So we can do that, and that should do a really good job of stabilizing these two atoms that are acting strange. We'll say that they need to have the same three-dimensional ADP. So these are carbon 63 and 69. And what if I haven't been clear, carbon 63 is on top of the inversion generated image of carbon 69, and since inverting an ellipsoid doesn't change it, we can say that this atom and this atom should have matching ellipsoids, and then that will also extend to this atom, and this atom will match as well. And since they're on top of each other, it's reasonable and not crystallographically crazy to say that they're going to match. So I'm going to fix that problem, or I'm going to implement that by typing EADP for equal ADP C63 C69. And I'm going to do that instead of our simu instruction. All right. And now how are we doing? Okay, now C63 and 69, they both look great. They look totally reasonable. Carbons 67 and 65 are now acting a little strange, to tell the truth. So maybe we'll use the same trick on them if it turns out that they're also right on top of each other. The answer is yes. Carbons 65 and 67 have symmetry generated pairs that are right on top of each other. Based on the same argument as before, the symmetry generated pairs are inversion related, so we can do the same EADP trick for C65 and C67. And now this tetraethyl ammonium looks absolutely perfect. I'm going to check these bonding distances one more time. The eyeball test says they're pretty good. Yeah, we have all our carbon-carbons right on 1.54 or so, and the carbon-nitrogens right on 1.51 maybe, so everything is great. At the end of this refinement, it would be nice to try to release these defix restraints and replace them with SETI or same instructions, or with nothing if possible. But I'm going to leave that for you to figure out. And I hope that this example of finding atoms in the difference map and then applying a few tricks to keep them stable even in the inherently difficult situation of symmetry equivalence on top of each other. I hope you can take this example and apply it to the next disordered tetraethyl ammonium and to the other examples in this problem set. Okay, thanks for watching.